Okay. I think we can start. So, so this week we're going to see a new data structure. I mean, a new abstract data type actually. And this is related to what we've seen in previous weeks. So it, so what we're going to be seeing today is something that looks like arrays and looks also like array lists, but it's actually more appropriate for doing recursion. So it allows us to do recursion more easily. And we're also going to be seeing some examples from recursion. So if we would just so remind ourselves what recursion means. Oops. So recursion is the following idea. You want to solve a large problem, and you basically say, okay, can I come up with a solution that I can apply to smaller parts of the problem and then get the results of those and get the solution to the full problem. So for instance, suppose we have two strings, string 1 and string 2, and we want to check if string 1 starts with string 2. Then we can say, well, let's look at the first character of the first string and of the first character of the second string. If they're not the same, then certainly this guy cannot be the beginning of this guy. Otherwise, so then we just return no. Otherwise, we say, okay, we have our strings. So this is string 1, and this is string 2. This is the first character, so this is checked, that it is the same. So basically, what I need to check is then that these smaller strings are one the beginning of the other. So if these two characters are the same, and then this string is the beginning of this string, so if this string here starts with this string, then the whole string I have here starts with the whole string here. Okay? And then this means basically applying the same reasoning to smaller strings. So this is the recursive step. And then finally, if the second string, this one is empty, then okay, the empty string is the beginning of every string, so we return yes. And if it so happens that the first string is empty and the second one isn't, then it couldn't be obviously that this empty string starts with a non-empty string, so we return no. And this gives a full algorithm. But what we said before when we were looking at strings was that we can define these recursive algorithms, but they're not very efficient because it's not very easy to break down strings in little pieces, in smaller pieces. So what we'll be seeing today is a data type that is called list, and it represents lists in a very specific way. So these lists are not part of Java, so we introduce them, and they're also generic. So a list can be of any type. So it's a list of type E. So let's see. So if we have a list of type T, then there can be two cases. Either the list is empty, so it's an empty list without any elements, or the list consists of two parts. It has a head element, and then it has a remainder. And this remainder is called the tail. So if I were to use this notation, I would say, okay, we have a head element and then we have another list. So this is the empty list. and this is a non-empty list. And this would be the head, and this would be the tail. If the list is of type T, then this means it contains elements of type T. And in particular, the head is an element of type T. The tail is a list, so it's itself a list of type T. Okay? So the notation we can use for list is, well, similar to the notation we had for arrays. It's just a sequence of elements. So I can write a list like this, and then if I were to write it in head-tail notation, so the head is 1, and the tail of the list is 5, 4, 2. Okay? Any questions up to this point? Yep. Which one? So in this, yeah, that's a good one. So the question is, when I say lists here, do I mean list or array list? So for this lecture, whenever I say lists, I mean lists. So it's just that I have forgot to write here lists. But yeah, I mean the notation for list and for array list could be the same. But in this lecture, when I talk about list, I mean list. Okay. Okay, so then you may ask, okay, if these lists are just sequences of elements, why did we introduce them this way? What's different than like having arrays or having array lists? And the answer is that what I've given you here is the abstract data type of a list. So it's basically how can you access the elements of a list. And you can only access the elements this way. Let's make this more precise. So what are the methods we have for in this class? So if ls is a list of type T, actually let's make this more specific. So say that ls is an integer list containing these 4 numbers. Okay? So if I write ls.head, then this will return, well, the head of the list, which is 5. Okay, this is also one. Okay. If I write ls.tail, well, then this will return the tail of the list, which is just 4, 2, 1. So this is what we saw. You can access a list by taking its head or taking its tail. So in particular, if you wanted to access the last element of the list, you have to do tail, tail, tail 3 times and then get the head. Then there is this constructor method, which allows us to attach a new element at the head. So if I say ls.const6, then this will return 6, 5, 4, 2, 1, which is the same as saying 6, and then the tail is 5, 4, 2, 1. So the only element to build oops, why did this happen? So the way to build a list is by adding elements, and you can only add elements like this at the front. Yeah. So if you like, this looks a bit like the stacks we had in Automata, where you could actually push things to the top of the stack and then pop them from the top. It's a bit similar. So you can only introduce things at the head of the list. Okay? And then we have another method is empty, and then this just checks if your list is empty. So remember, ls is this list, so ls is empty will return false. And finally, I have a static method that allows me to construct new lists. So if I say list, I don't know, integer, empty, this will return an empty list of type integer. Okay? Sometimes it will be dropping the type notation here, so leave it the compiler to figure this out. So for example, if I have a list ls that is not empty, I can take its tail, and then I can put cons, and then get back the head. Now, all the operations we've seen here are constructed. So these will not actually change ls, we just return the head of ls. This one, again, will not change ls, it will just return a new list, which is just the tail. And similarly here, this will construct a new list, that is the old list plus a new element. But the old list remains as it is. So in particular, if I have ls, so this is non-empty, I can take its tail, and then I can cons it, so I can put in the front the head of ls. So if you like, I have a list like this. I take its head, so I write it as h followed by head, and then I say, okay, this is, well, basically what I say here is that you take the head, the tail, and you attach the head back. So what I want to say is that these guys should be the same. You have a list, you take the head, you take the tail, and then you put them back together, obviously get the same thing. Any questions? Okay. So these are all the methods. There are no other methods, there are no constructors. The only way to construct lists is you start with empty by this method here, which we call actually factory method because it creates new objects. And then you can add elements with the cons. So this is a bit similar with array list, but for array list, if you remember, you had to call a constructor, whereas here, you call the factory method. Okay? Okay. So now that I've been giving the description of list, so this, in a sense, is a full description of what this data type does. And we introduced it this way. I mean, we introduced this list in order to also introduce the idea of an abstract data type. So this is something that we give to you. I mean, if you look at the exercise afterwards, you get some class files, but you don't get the code. So you get these objects, and, well, you don't know so much about them apart from how can you access them. And how can you access them is by the method I showed you. And this is like, this captures the general idea of an abstract data type, which is defined only by its methods, and how these methods can make the objects of this data type interact with other parts of the code. So it's important not to confuse this data type with how it's actually going to be implemented, which is going to be by some data structure based on linked lists or arrays. We're going to see that afterwards. For now, what we're only interested in is in the abstract description, which is the methods you can use well, to actually access and use these lists. Okay? So coming back to sum up the properties we have. So a list is simply a list, a sequence of elements, if you like, of a given type. How can we access its elements? We cannot say go to the element at the ith position. We can only say get me the head or get me the tail. And another important aspect is that lists are immutable. So when you code these methods as we saw, so the methods are here, you don't actually change the list you call them upon. You create a new list. Another important aspect is that an empty list is an object that happens to be empty. So in particular, is not a null object. Incidentally, there was an error in the notes saying that the empty list is null, but yeah, that was a mistake. And then we have also provided some other methods. So you have this method to string, that if you give it a list and you say, okay, list to string, it returns a string representation, and then if you put this in a printf method, it actually makes conversion. If you put a list in a string method, in a print method, it makes automatic conversion. And we also have this helper method that you give it a string that represents a list of integers, like in this way, and it gives you back an object that is a list of integers. Okay, any questions? Okay, maybe we can see then a demo. How can I do this? Okay, so I have my code here. That didn't go very well. Okay. This is a bit stretched. Okay, let's see the code first. So I'm creating a scanner object, and then I declare a list and then basically I'm going to input it from the standard input as a string, and then I'm going to use this parse int list to convert it to to a list object. So let's see if I compile, and then actually I think it's going to be easier like this. Okay, so if I say Java, okay, let's see. So this is my list. And obviously, okay, so what happens here, so the code passes it and returns a list object, ls. And then I call to string, on it, so it converts it to a string, and then you print it. Okay? And then you get back actually the same thing. Now the next thing I do is I say, okay, I don't need to call to string, I leave it to be done automatically, so I just say, okay, just print ls, and then it will print the same thing. And now what I do next is, okay, let's take the head, it's going to be an integer, let's take its tail, it's going to be a list for integers again, and okay, so here it is, the head is this, and then the tail is this one. And now I say, okay, can I use cons to get the head of the list, that is t, and then cons back the head? So I can do that and get back the original list. Yeah, it's not great the numbers are put in this list, but anyways. And this is like the recomposed list. And now next, what I'm doing is I'm creating an empty list. And then I'm going to check if this is null or empty. So ls0 is an empty list. And then I do a check for null, and it returns false, because it's an object, it's not null. But if I do a check of is empty, this is going to return true. Okay? So this is just playing with the methods we saw before. Okay. Any other question? Any questions? Okay. So I said it's easier to, so we introduced this data type in order to demonstrate recursion. So let's see. If I want to write a method that operates on lists, like list lists, then I can consider two cases. What should the method do if it is an empty list? Well, and what should it do if it is a non-empty list? And then remember that a non-empty list is just a head and a tail list. So a recursive method then can do the following. We can consider, so let's say a non-empty list is h ls. And I want to define a method meth. Let's call it method. Well, then I can say, okay, what should happen if I code method on ls? And then how can I combine h and the method and the result of this to get what the result of this one should be? So consider what should happen when I apply the method on the tail of the list, and then I see how can I combine the head of the list, the previous result, to get a result for the whole thing. And when I do that, basically I have a full solution. Okay? So let's see this through an example, maybe it's easier. So I want to add all the numbers that I have in a list. So there are two cases. If the list is empty, what should be the sum of all the elements? So this is a list of integers. Any ideas? So let me repeat. I want to get the sum. So I have a list that contains integers, and I want to sum them up. So the question is, if the list is empty, what should the sum be? So it should be 0. Suppose I have now a list that is not empty. It has a head and a tail list. Then I could say the sum is, well, simply get me the sum of the tail and then add the head to it. So it's h plus the sum of the tail. And that is actually a full solution. And we can write an algorithm for it quite simply. So remember we said for the empty list we get 0, and for a head ls we get head plus the sum of ls. So how does this translate into implementation? Well, we say, okay, you're given a list ls. If ls is empty, return 0. Else, so if this is not the case, you go here and you just return the head plus the sum. Remember, this is the same method applied on the tail. So I could have written an iterative solution that goes through all its elements and remembers the sum, and then each time adds the new head to the sum. But what we have here is that, I mean, we have an implementation, an algorithm that is actually more intuitive to explain and to write down. So that's what recursion actually helps you. It's like helps you to write simpler algorithms. Okay. Now, the second thing I want to check is whether a single specific item is a member of a list. And I can say again the same. If my list is empty, then is item an element of it? Well, no. So I say, well, it's false. If my list is not empty, it has to be of this form. So then I say the following. Well, if H is the item that I'm looking for, then return true. If not, then just check whether item is an element in the tail. So I have a list, it has a head and a tail, I'm looking for an item. If the item is the head, I'm done. Otherwise, I throw it away and then I search for the rest of the list. Okay? Let's see. So I said, if empty, return false. Should have been in here. If I have HLS, return, well, true. Otherwise, check that item is inside the list. And how can I implement this? Well, as follows. If the list is empty, I return false. Otherwise, if the head equals to the item, I return true. If that is not the case, then I'm here, I have to do recursion. That's okay, return is in. I should have written this is in, not check. Anyways, is in, well, and now check the tail for the item. Okay? And now finally, how can we change elements inside the list? Well, suppose I want to change, and I have my ls, and I have p and q. I have two cases. If ls is empty, so what I have a list ls, and I have two elements, p and q. Sorry, I have two objects, and I want to take a new list that every p has been replaced by a q. So I want to make this change inside my list. Not that this is going to be constructive, it's not going to change the list, it's going to create a new list that is exactly like the old one, but it has changed its p into a q. Actually, let's make this more concrete. Let's say that this is, write again with numbers. So I wanted to change ls, and I want to change what? Every 1 into 42. So if ls is the empty list, then there's nothing to change, I'm done. If not, it's going to be some h ls. Now I use the same ls, let's write ls prime actually. And then what do I need to return? Well, there are two cases. If h equals 1, I return 42, and then I attach to it the change of 1 to 42 on the tail. So basically say, okay, take the tail, make all these changes, and then when you come back, don't put 1 back, but put 42, because I want to change 1 to 42. So this is if h equals 1. If h is not equal to 1, I say, okay, then leave h as is, but make this change to the rest. Okay? Okay, so here I have an implementation of this. Basically, the implementation in this case is quite simple when you have written down the pseudo algorithm, because, well, basically you write down in code exactly what you have up there. So let's see, so I want to change ls with p's going to q's. It's okay, if the list is empty, then return the empty list. So here actually I could just say return ls, but yeah, I create a new list and return it. Well, okay, this is, yeah. I could create a new list, or I could give the old list. The fact that lists are immutable allows us sometimes to return the same list, but anyways, let's be constructive and returns an empty list. Then I say, okay, let's apply the change to the tail So since it's not empty, then I'm here. So if it's empty, I do that. If it's not empty, I continue and apply the change to the tail. So I do this, and this gives me t. So t is this one here. And let h be the head of my original list. So it will be this one. And then it's okay, if h equals to p, then return t and add in the front q. So change p to q. Otherwise, just return t, add in at the beginning h. So this is the first case, and this is the second case. Okay? Any questions? Okay. So I can go back to my demo then. I haven't done much else here apart from, oops, no. So I had some more code here, and that says, oh, this is iteration, let's forget about this. So I have here the implementation of change as we saw it before, and then, okay. So if I change in 1 to 42, I get the same list as before, but the last element from 1 is going to 42. I have actually another example of iteration, but I'll come to this later. So, yeah, so basically I'm just demonstrating that what I just saw you works. Okay, that wasn't particularly interesting. Come on. Okay. Okay, so that's what I want to say next. So we saw this example with these examples with recursion. So then the question you might question is, okay, why not do iteration? Can we not do iteration on this? And the answer is we can do iteration. There are two problems. One problem is that sometimes you might find the iterative solution not as easy or intuitive as the recursive one. And another more, well, let's say, and the nasty problem is that when you have a list that's already constructed, let's say 5, 4, 2, 1, you can access its elements from left to right. Because you say head, and then you get the tail. So you access first 5, then 4, then 2, then 1. But then if you have an iterative solution, so goes through the list, and then constructs a new list, so suppose that you want to change, I don't know, you want to change 4 to 6. You will start from 5, you say, okay, 5 doesn't need change, so let's put it back. You arrive at 4, you say, okay, 4 has to be changed. It has to be changed to 6. 2 can remain as is, 1 can remain as is. So what happens is that if you go access like this, when you want to actually construct the list, you have to go this way. Because you start with the empty list, you put the first element, it becomes 5. You put the same elements, it becomes 6, 5. You put the third element, it becomes 2, 6, 5, and then so on. So what we get here back is the same, well, it is the result we want, but it's the reverse list. And this has to do with the fact that this list, you can access them, you can put things in the front and then take things from the front. But this means that when you read and write into a list, you get the reverse result. Is this clear? This is very much like stacks in automata when we're seeing that. If you read from the automata and push back, you get it reversed. So the code I have here for changing iteratively goes as follows. It says, okay, let's start with the empty list. And then I have a for loop that goes through the list, ls1, until it's empty. And each time it gets back the tail of the list. You start with the full list. If it's not empty, get its head. If the head is p, then you say, okay, this ls2 that I started constructing, then put back q. So if P is not equal to the head, then you put back the head to what in ls2. So you basically, you traverse the list, and then you create a new list as you traverse with these changes applied. So this applies just the changes. But as we said, because you traverse the list from left to right, and you construct from right to left, you will get, well, the list that you want, but reversed. So this will work, but it will create the list reversed, so then you have to reverse the list. And how do you reverse a list? Well, by reading and writing it back. So you create a new list, ls3, which is empty, and then you go through the list you constructed, ls2, until it's empty, and each time you update it with tail, and you just say, well, ls3 is what it was before with the header of ls2. And this actually works, because if I have the list like this, so before it was what? 1, 2, 6, 5. So this is my ls2. ls3 is initial empty. Then I read this way, remember? So then from empty I get back, the next time is 1. The next time is 2, 1. Then becomes 6 to 1. And then 5, 6, 2, 1. Remember here that ls1 was 5, 4, 2, 1. Okay? Any questions? Okay, so iteration can be done in lists. You use loops of this kind, but you have to be careful that you might get back reversed lists. So here in the example I had, actually, now I remember that there was a reason this example was here. I have written another way to sum the elements of the list, which is here, where it says, okay, let's have an accumulator, so just an integer that remembers the sum of the elements of the list. It starts from 0. I do this for loop as before. This time I create a new list to do the for loop, ls1, because I don't want to change my variable ls. So okay, you start from ls1 being ls, and until it's not empty, you just add to the accumulator the head of ls1. And when you go through the loop, you just update ls1 to be its tail. And then this will sum up the content. So here, when we run it, well, it returns a number. Obviously, it's a bit difficult to figure out what this is. Let's make it just a bit simpler. So I guess the sum should be 21, which is just about right. Okay. Any questions? Okay. And now the next thing I would like to talk about is how to sort lists. We're going to see two different methods here and two different algorithms. There's one more algorithm in the notes. So the first recursive algorithm is the following. How can I sort a list? Well, if the list is empty, it's very easy to sort it because, well, you just return the empty list. If the list is not sorted, if the list is not empty, it's going to be a head followed by a tail. Then what you can do is you can sort the tail and then take the head and insert it inside the sorted list in position. So you sort and then you insert. So this is insert. Okay? So this is a recursive solution so long as we define what insert means. So how can we insert an item into a sorted list? Well, again, if the list is empty and I want to insert an item, well, let's call it item. Let's call this ls. Well, I just return item as a list. Otherwise, if my list is of the form head followed by a tail, there are two cases. If my item is less than the head, then I can just say, okay, put item, then put head, and then put ls prime. And this is if there's not much space here. So I'm going to write it well, if item is less than head. So if item is less than head, what should I return? I should return this. Otherwise, so if item is greater or equal than the head, well, I say return the head, and then whatever you get by inserting item to the rest of the list. So this algorithm you might have seen before. Well, it's nothing more than insertion sort. Okay. And actually, here is the code for it. I'm going to go through it just quickly. Maybe I can leave this here and then go to here the code here. See the code. If the list is empty, I just return the empty list. Otherwise, I insert the head in the sorted tail. And how do I do the insertion of an integer n in any a list ls1? Where I say if it's empty, return the empty list, and then, well, the list containing just n, which is empty list const n. Otherwise, take its head, h. If the head is greater than the item, the n, then well, just return the, sorry, I got confused. Yeah, the original list ls1, and at the beginning just add n. So it was this one. So this is my whole list, and then I just add the element, well, item, which here is n, and I return it. Otherwise, okay, I say, why don't I insert first my element inside the tail? I get an ls2, and then I put back in the front h. So I return this one. Okay? Okay. And then another sorting algorithm is quicksort. So quicksort is a very fast algorithm for sorting. It's again a divide and conquer algorithm. Well, it's the first one we see. So what happens if we have a non-empty list? So if you have an empty list, it's very easy to sort it, just the empty list. If it's not empty, so the list is going to be what? H followed by the tail. That's okay. Let's put this aside. Let's call this pivot actually, and break down ls into two parts. ls1, which are all the guys that are less than pivot, and ls2, which are all the guys that are greater or equal than the pivot. So I take ls, I break it into parts. The parts is not that I break them like a specific point in ls, I just break them using this. So this is ls2, using this criterion. And then, how can I sort the whole list? Well, I can say the following. Let's sort ls1. All these guys are less than the pivot. So put this, and now do this operation here, which is called append. I'm going to explain it in a bit. And then append it to the list that has the pivot, followed by the sorted ls2. And what is this append operation? Well, if I have the list 1, 2, 3, and do append 4, 5, 6, then maybe you have guessed it just means merge the two things. So this is what append does. So you can see again the description of the algorithm is very simple, at least at the pseudo algorithm level. It just says, okay, I have a list, I extract the head, I have then a smaller list, now I break it into parts, those that are less and those that are greater or equal. I sort these guys, and then I come back and join them. Okay. So how is this then implemented? again, we'll have to look at this rather quickly. Okay, the list is empty, or it just contains one element. So if the tail of the list is empty, there's nothing to do, I return ls. In this case, I didn't look just at the case where I have an empty list. It's also important that yeah, actually, that we might have worked even without this. This is just for efficiency. If you just have the one element list, how can you sort it where you just give back the same list? It's already sorted. Okay. Otherwise, let's take the head, and this is, we call it pivot. Take ls now to be the tail of ls, and then create ls1 and ls2. And then you go through ls, and and then you say, okay, I go through the elements of ls. So this is by getting the head. If the head is smaller than the pivot, I put it in ls1. If it's larger than the pivot, I put it in ls2. I sort these guys with the same method, so this is the recursive call, and then I append. Append is a method we're going to see afterwards how it's implemented, but it does what we said. So append ls1 with ls2 with pivot in the front. Okay? Okay. So in all these recursive examples, we have recursive method calls. So for instance here, we had sort being called back with ls1 or ls2. So it's important to note here that the recursive call will have its own environment. So when we go back and make this recursive call, this ls1 will be actually this ls here. So this is important in order to understand how the recursive calls will work. Of course, you can have aliases. The variables of the recursive call may be aliasing variables of the original calls, but it's important that they run in distinct environments. So you can only intersect these environments to aliasing. And obviously, when the method call finishes here, so the recursive call of this one would have ls being ls1. When you come back, ls becomes the old ls. Actually, in this case, we had already changed this to ls tail. Okay. And another example is how can we append a list to another one? Let me see a bit in more detail. So it says how you can append ls2 at the end of ls1. So how can you merge ls1 and ls2? Well, if ls1 is empty, you want to append another list to the empty list where you just get the other list. So if ls1 is empty, you just return the other list. Otherwise, get back its head. So we have ls1 equal head ls1 prime. How do I append? We say, okay, append the ls2 to the tail of ls1. So append ls2 to the tail of ls1, and then put h back, and return that. So actually we can see through an example. So what is my example here? So I want to do append ls1, ls2, where these are the two lists. So the first time I call this, I have ls1 equal 1, 2, 3, ls2 equal 4, 5, 6. The head is the head of ls1, so h equals 1. And then this makes a call to append, but now we have the tail here. So I make another call of this one, but ls1 has been replaced by ls1 tail. So the new call, so this makes another call. Sorry, in this case, ls1 is this one, ls2 is this one, and then we get the head of ls1, which is in this case is 2. And now we have, okay, make another call to append. So we make a call to the tail of this list. ls2 is this one, And what is the head? Well, the head is 3. Now we have another call. In this case, ls1 is the empty list. ls2 is this one. And now observe that since it's empty, we just return 4, 5, 6. And now these returns are propagated at the top, and then we get the result we want. But it's important to note that these are calls of the same method, and they run in different environments. Okay. Any questions? Okay, so finally, two things I want to talk about is how do we know that your recursive method works? Well, you write it down, it might do anything. Well, you just, because the recursive method, you have the base case that you write in the recursive one, where you just need to check that the base case works, and then in the recursive case, if the recursive calls of the methods work, then your method works, then that's fine. It's like induction. Actually, yeah, it's similar to induction in numbers. Okay. And then, in all the examples we saw, apart from is in, you had the recursive call and you get the results and then do something with it and then return. And that is called recursion. But in general, more specifically, you could have tail recursion where you just return the result of the recursive call. And here, okay, we don't have time to see this in very detail, but if I want to check the sum of a list, I can have this recursive method that has an accumulator, and if the list is empty, it returns the accumulator, otherwise return the sum of the tail of the list, and it passes inside as an argument the accumulator head. Anyways, I think we have talked about this before in arrays, so we can have tail recursive solutions, and these are very close to iterative solutions, which we had saw before. Anyways, I think we're out of time, so let's sum up. So what we saw today is, well, an abstract data type that is particularly useful for writing recursive algorithms. It's immutable, so all operations that we write are constructive. It's easy to use with recursion, but you can use them with iteration as well. And then, what does it mean to solve a problem recursively? It means you apply your method to smaller parts of it, to smaller problems, and then you put them together to get a solution. Okay. So that was all for today. Do you have any questions? Okay. Thanks.